smallest sign changes. So I would change the epsilon 1 to minus, and I would change the epsilon 2 to plus, and calculate how many sign changes.
Oh shit, one more time, I missed that.
Okay. I would change now the epsilons
To the minimum.
whatever sign has the smallest number of sign changes. So here would be minus, and here would be plus. Would give me 0 sign changes here and 0 sign changes. And then I would change how many sign changes do I have now. That's the number of course difference. Okay.
So you wrote difference between
Why didn't he say that?
epsilon I
What?
greater
First
than
time.
0 and
Why didn't he
less
say
than
that
0?
the
Right.
Be real roots, not positive real roots.
The real part is the number of 0 positive real roots. That means.
It was flat.
Oh, okay.
Take the positive parts. There you go.
Oh,
Since you said that was positive.
yeah, that was bad. That was very bad. 0 roots, number of roots, number of 0 real part roots. That's what I said. I said positive there, I should have been that. Real part roots. Does that make sense?
This is just the root.
It's the number of 0 real part roots. Yeah, okay, now it's correct.
Those are completely complex. It's strictly complex.
If there are 2 of them, it's a complex conjugate pair. You're correct. If it's 2 of them, it's a complex conjugate pair. If it's 1, it's actually a root at 0. Okay? So the root array gives us immediate calculation stability. Kevin, you lost me? Hey, no, okay. Kevin, you lost me?
So how many real part? Zero real, how many real part?
In this case, 1. Because if I change this to minus this plus, I have only one sign change this one. The minus and plus. That's the only minus. So this example had 6 roots, 3 with 0 real part, 1 with positive real part, and 2 with negative real part. All that clear? No? Nate, okay? Claudia? All right. David, okay? All right. So, that can definitely always be used for open loop stability, no conditions. Because the open loop transfer functions have polynomial as denominator. So, remember that part of the exam is pen and paper. So if in pen and paper exam 2, I'm giving you a polynomial, and I want you to find open loop stability, and I'm not allowing you to solve it with a calculator, what do? Root array, without me having to say the method. Now, what about closed loop stability? E to the minus ds messes up things. Let's say I had, for example, first order plus time delay transfer function. Let's say g of s equals and let's say I have, let's say a pi control. Let's say gc equals kc 1 plus 1 over pi. This is first order plus time delay, and this is a pi control. By the way, let me introduce the terminology here. Well, okay, let me first write this and then introduce the terminology. So the denominator of the closed loop transfer function is the denominator of closed loop yes is 1 plus gu gc. In other words, 1 plus kc over tau s plus 1 e to the minus ds. And I can rewrite this one as kc, and I can rewrite that as tau I s plus 1 over tau I s. And the root of that is setting that equal to 0. Okay, so poles solutions of 1 plus GU GC equals 0. And we can make common denominator. And we have tau s plus 1 from this part plus times tau I s from here plus kc, oh, oops, k, not kc. There's an extra c, sorry, take that out, yes, k, plus k from here, kc from here, tau I s plus 1 e to the minus ds equals 0. That's the numerator I wrote. Obviously, numerator of the denominator equals 0 means numerator equals 0. So that's the roots that must have negative real part to be stable. Because of this, not polynomial. We have a nice if it was polynomial, very nice if it was polynomial. But before I go on, let me treat a term. With some terminology. So, the closed loop ds have denominator right? Again, I'll repeat 1 plus product of everything in the loop in general notation, okay? In our class notation, everything in the loop is GUGC. In the picture on top. Picture on top, everything in the loop is GUGC. So 1 plus product of everything in the loop is 1 plus GUGC. So they have denominator 1 plus GUGC. You can see it here, you can see it here. Okay? So the closed have denominator. So the closed loop poles are the roots, and now I'm introducing terminology. This is called the characteristic equation. One plus du gc equals. So that equation, denominator of closed loop transfunctions equals 0, has a specific name. It's called the characteristic equation. So the closed loop poles are the roots of the characteristic equation. So that's what I wrote here. That's the characteristic equation. That equals 0. And saying that's the characteristic equation. And that can be written this divided by tau s plus 1 times tau is. And of course, numerator of the denominator equals 0 means numerator equals 0. But it's not polynomial. So, any ideas e to the minus ds makes it not polynomial. Any ideas how we can approximate e to the minus ds to make it polynomic? All the same. Excellent. Great. That seems like a great idea, except it has important problem. It has a serious problem. Let's take the first order plus time delay. What would be the Taylor series expansion of e to the minus ds? variable, so obviously we're not doing the S. We're going to Taylor series expansion on what? On the delay, right? And
What?
hmm?
I thought it would be S. You do Taylor series.
No, on the delay because we want a function of S. It's a function of S.
Okay.
Okay. You do. Anyway, we'll do it on a delay. And if we do it, for example, on D equals 0, I could approximate that as e to the minus 0s plus d e to the minus ds with respect to d at d over yeah. At d equals 0 times d minus 0. First of all, it's Taylor series expansion.
Isn't S the variable?
That's what I thought.
No, we're using
That's what I
D
would've
as a
done.
Taylor series expansion.
These are, I don't understand. You would have done S too? Yes.
S has no particular value to expand. S can be anything, remember? S is anything in the Laplace domain. Anything that works can take as S. It's not something with a specific value. D is something with a specific value. So that gives me e to the 0 is 1. Derivative of e to the minus ds with respect to d is e to the minus ds times minus s evaluated at d equals 0 times d, which is the same as 1 minus, this is at d equals 0 is 1, so minus d times s. With me? Which means that GU could be approximated, which if GU is k, for example, of the tau s plus 1 e to the minus ds, it would be approximated by k times 1 minus ds over tau s plus 1. With me? That would be approximation. Don't keep detailed notes on that because this will not work. Okay? I'm just showing you why this really good idea.
What? The hell have I been cooking?
I'm just showing you why this really good idea has a serious problem. How many poles and how many zeros does this guy have? Same. 1 pole, 1 zero. A transfer function that has 1 pole and 1 zero would predict that for a finite input, you get infinite output. It's not realistic. That drastically changes the predicted system response and everything else. So whatever we do in the approximation, we cannot change the difference between poles and zeros. Okay? This would have, a response to a step change would be an impulse. Would be infinity. So that's an obvious, very serious problem. So, any ideas? Taylor series expansion is a good word. Can we figure out perhaps a clever way to do the Taylor series expansion without changing the pole excess, the number of poles minus the number of zeros? All right, I think that's been enough time. So I'm very happy you came with saying Taylor series expansion. So that's not a good, that will not work. But here's what we can do. Now take notes. And this is called the first order Padé approximation. So we're going to do the first order Padé approximation. So we have that pesky e to the minus ds. We can that e to the minus ds is the ratio e to the minus d divided by 2s over e to the plus d divided by 2s. Okay, that's not an approximation, that's exact. And now, approximate each of those as first order Taylor series expansion. So, this becomes e to the minus, this becomes e to the, so approximate now, e to the minus d over 2s, approximated at d was 0, you get 1, okay, so yeah, e to the at d equals 0 plus derivative of e to the minus d over 2s with respect to d at d equals 0 times d minus 0, and the denominator would be e to the plus d over 2s at d equals 0 plus derivative of e to the plus d over 2s with respect to d at d equals 0, d minus 0, which is approximately equal to, at d equals 0, get e to the 0, so 1. The derivative of the exponential is the exponential times the derivative of the exponent, which is minus s over 2. All that evaluated at d equals 0 times d over 1 plus, same thing with the plus, e to the plus d over 2s. So I'm handwriting the derivative. Times plus s over 2. All that evaluated at d equals 0 times d, which will give me 1 minus d over 2 times s. I don't want to have any confusion, so let me write ds over 2. Divided by 1 plus ds. Okay? So that's the first order Paternos. Now what happens to first order plus time delay? So now if I have GU equals K over tau s plus 1 e to the minus ds, that gets approximated as K over tau s plus 1, 1 minus d over 2s. How many poles? How many zeros? 2 poles, 1 0. And where is that 0? What kind of 0 is it? Where is that 0? It's positive. What does that mean for the response of that system? Inverse response. So here is the true response of first order plus time delay. Let's say here is